Every time you see a hot piece of metal glowing, you're actually looking at a mystery that once had the world's greatest scientists completely stumped. That simple glow held a secret so deep that when we finally figured it out, it didn't just solve one puzzle. It completely shattered our understanding of the universe and gave birth to quantum physics. I mean, you've seen this 1,000 times, right? The burner on an electric stove, coals in a fireplace, maybe you've seen a video of a blacksmith working. As things get hot, they start to glow. But have you ever really stopped to think about why? What is physically happening in that object to create light? And why does the color change? You know this progression intuitively. The hotter something gets, the more that color shifts. It goes from this dull red to a brighter orange, then to yellow, and if you get something incredibly hot, it becomes a brilliant, dazzling white or even blue. And it's this connection, this link between color and temperature, that's the absolute key to our whole story.
So, to really get to the bottom of this, physicists knew they had to simplify the problem. I mean, real-world objects are messy, right? They reflect some light, they have different textures and compositions. So they did what physicists do best. They imagined a perfect object, an ideal case to test their theories on.
And they called this ideal object a black body. Now, the name is a little misleading because it's not always black. It gets that name because it's a perfect absorber. It soaks up every single bit of energy, every wavelength of light that hits it. Nothing gets reflected. And here's the beautiful part. A perfect absorber is also a perfect emitter. The light it gives off is pure, depending on just one single thing, its temperature. So how would you even make one of these? Well, a really great real-world approximation is to take a hollow box and poke a tiny little hole in it. You see, any light that goes into that hole gets trapped. It just bounces around and around on the inside walls until it's completely absorbed. This makes the hole itself a near-perfect black body. And the radiation that eventually leaks back out of that hole, that's pure black body radiation. And what's so amazing is just how universal this is. At about 798 Kelvin, pretty much any solid object starts to glow with that same faint red. By 1000 K, you've got the clear, visible red you'd see in a kiln or a lava flow. Even our own sun behaves almost exactly like a black body. Its surface temperature, about 5800 Kelvin, is what gives it that familiar yellow-white light. In every single case, temperature dictates the color. It's that simple. So, this all seems pretty straightforward, doesn't it? Hotter equals bluer light. Simple. But when scientists back in the late 19th century tried to explain why this happens using the physics they knew and trusted, well, they didn't just hit a wall. They hit a huge one. They took their most powerful theories, we're talking thermodynamics and electromagnetism, the absolute bedrock of 19th century physics, and they used them to predict what the light spectrum from a black body should look like. The math was solid, the theories were trusted for everything else, but the result they got was, well, it was completely absurd. Okay, so here's where it all just fell apart. The classical theory predicted that as the wavelength of the light gets shorter, as you move past blue into the ultraviolet range, the amount of energy it radiates should just skyrocket, heading straight for infinity. But that's not what happens in the real world at all. Observations clearly showed that the energy peaks at a certain color and then drops off to zero at shorter wavelengths. The theory wasn't just a little bit wrong, it was predicting infinite energy coming out of a warm object, which is just impossible. This disagreement was so complete, so total, that it earned one of the absolute best names in the history of science, the ultraviolet catastrophe. And that name tells you everything. It was a signal that something was deeply, fundamentally broken at the very heart of physics. So, what happened? Where did the world's best theories go so wrong? These were the ideas that built the Industrial Revolution. They worked for steam engines, for electricity, for everything. What on earth was so special about the simple glow of a hot object? The answer came from a physicist named Max Planck. He decided to try something that, at the time, must have sounded like complete heresy. He started questioning one of the most basic, fundamental assumptions about how energy itself actually works. You see, for centuries, physicists had always pictured energy as being continuous, like a smooth ramp where you could have any possible value. It could flow smoothly from one amount to another. But every time Planck tried to make the math work with that idea of a smooth energy ramp, he kept crashing into that same impossible wall. So he made this really wild suggestion. He said, what if energy isn't a smooth ramp at all? What if it's more like a set of stairs? What if energy can only be emitted or absorbed in tiny, discrete packets, which he called quanta? So an object could spit out one packet of energy, or two, or three, but never, ever 1.5 packets. Energy itself was chunky. Now, at first, this probably just seemed like a desperate mathematical trick to get the right answer. But when Planck plugged this idea of chunky energy into his equations, the catastrophe just vanished. Why? Well, because to produce that really high-energy ultraviolet light, an atom would need to emit a single, huge, energetically expensive packet. And that was just way less likely to happen than emitting a bunch of smaller, cheaper packets of red or yellow light. Suddenly, the theory predicted the energy would drop off, perfectly matching the data. By making energy chunky, he had fixed physics. And in doing that, Planck had almost accidentally kicked open the door to a revolution. This tiny idea of quanta was the very first step into the bizarre, counterintuitive, and absolutely amazing world of quantum mechanics, the theory that would define all of 20th century physics. But here's the thing. This isn't just some dusty old story from a physics textbook. Planck's discovery gave us a whole new way of looking at the universe. And it turns out the fingerprints of black-body radiation are literally everywhere, from the vastness of the cosmos right down to our own bodies. Take this number, 2.7 Kelvin. That's just a couple of degrees above absolute zero. It's the temperature of empty space itself. It's the faint afterglow of the Big Bang, something we call the cosmic microwave background. And when we measure its spectrum, it is the most perfect black-body curve ever observed in nature. The echo of creation itself obeys Planck's law perfectly. Okay, how about this number, 254 Kelvin? Using these very same laws, we can treat the entire Earth like a giant black body, absorbing heat from the sun and radiating it back into space. If you do the math, Earth's baseline temperature should be a chilly -18 degrees Celsius. The fact that we're warmer than that is proof of the greenhouse effect. But the whole calculation starts with this fundamental law. And it's not just out there in space. It's right here. You, right now, as you're sitting there, you are glowing. Because your body has a temperature, you are emitting thermal radiation, just like a black body. Of course, you can't see it with your own eyes because it's mostly in the infrared part of the spectrum, but that is exactly what a thermal imaging camera picks up. And finally, let's take this idea to its most mind-bending, extreme conclusion. Stephen Hawking's incredible insight was this. If a perfect absorber has to be a perfect emitter, well, what's a more perfect absorber in the universe than a black hole? This led him to propose that even black holes must radiate. This theoretical Hawking radiation would have a perfect black body spectrum, which means the blackest things in the cosmos aren't actually black at all. They glow. And that leaves us with a final, staggering thought. If black holes are constantly, even if it's incredibly slowly, radiating their own mass and energy away, does that mean that over unimaginable lengths of time, they could eventually just evaporate completely, fade away to nothing? And to think, that idea, that question about the ultimate fate of the universe, all started with something as simple as the glow from a hot piece of metal.